All right, mathletes, here we are looking at exponential growth and decay. So we know that we are going to be talking about exponential growth. Okay, when we're looking at our base value, and if that base value is greater than 1, we're going to see growth. Okay, and we've also called that an increasing function, but in word problems, it's going to be growth, and a decay if it's between 0 and 1. We've also called that a decreasing exponential function. Okay, so with these functions of growth and decay, usually we're going to be dealing with this variable here. We've called this variable b in class, but remember that variable is a dilation, okay? And it's going to stretch our graph vertically, okay? Which is also going to affect our initial, okay, condition, okay? So here we're looking at an example of population growth. Okay, so we're looking at about 100 rabbits, and we're talking about that the population doubles every month. Okay, so population also doesn't grow at a constant rate of change, but it grows exponentially because as you get more people in the population or more rabbits, those are also increasing in production. So you're not just getting a constant rate of 50 more rabbits every day, but those 50 more rabbits you had or the 100 more rabbits you had the month before, they're also going to reproduce. So you have this exponential type thing happening. So in this example, we see 100 is the initial amount of rabbits we have. So this is also going to be closely tied to our initial value. Okay, and then our b value, because we're dealing with growth and because it's doubling, we have a 2 here. So we can see to find the population after 3 months, we can substitute t, our time, and 3 into our function, and we get 100 times 2 to the third. Well, 2 to the third is 8, so 1,000 or 100 times 8 is 800 rabbits. We can also do it for partial months using the equation. So if t equals 6.5, we can put 6.5 into the equation, and we can see that 2 to the 6.5 is 90.51. Times that by 100, and we get 90,051 rabbits after 6.5 months. So growing very quickly. So let's look at an example here. So a locust plague, the area of the land eaten n weeks after the initial observation, is given by that function. Okay. So find the size of the area eaten initially. Well, initially, remember, that's when our n is equal to 0. Okay. So when we have n equal to 0, we have 8,000 times 1.4 to the 0. Well, anything to the 0 power is equal to 1, and we get 8,000. And again, like our previous slide, our value in front is usually our initial condition. Okay, so what would it be after 4 weeks? So that's if n is equal to 4. So if we do 8,000 times 1.4 to the fourth using my calculator, so 8,000 times 1.4 caret 4 raised to the fourth power, we're going to get a population of locusts at about 30,733 rounded to the nearest locus. So as I come over here, after 4, I'm going to be at about 30,800, so I'll be somewhere around there. Okay, now find it after 7 weeks. So I do 8,000 times 1.4 to the 7th. Putting that into my calculator, we see that this is going to be 84,331. Okay, so after 7 weeks, 84,331 is up there, and we get a function of growth connecting our 3 points. So we can sketch our graph. Okay, so along with growth, we're also going to talk about decay. So decay is an exponential decreasing graph over time. Oftentimes we talk about decay when we're talking about cooling. So as we introduced something in a room and it's hot coming out of the oven or a cup of coffee, it's going to cool down, and it's going to cool down exponentially. We have radioactive decay, which is used to age turn certain things, and the drop in current when we're talking about electrical appliances. So when appliance turned out, they have a certain amperage, and then it dwindles off as that circuit has been turned off. So let's look at an example here. So the current I flowing through the electric circuit in a fan T milliseconds after it is switched off, okay, is given by this function. Okay, notice that our A value, 0.7, is less than 1, so we are expecting a decreasing exponential function here. So the initial current in the circuit, okay, so that's when T is equal to 0. Well, we know that's going to be 320. So we have our initial current in the circuit. Okay, so after 4 milliseconds, okay, we can go ahead and do 320 times 0.7 to the fourth. And as we use our calculator, we get 320 times 0.7 caret to the fourth. We see that there's about 76.8 milliamps left. So 76 is going to be somewhere in there. Okay. And then after 10 milliseconds, we do 320 times 0.7 to the 10th. Again, using my calculator. I'm going to see that this is now down to 9 as my current. So at 10, we're down to 9, so we're getting really close. Okay, and as we draw this out, it's going to reach our asymptote here at 0. Okay, that is going to slowly lose its current over time there. Okay, this concludes our notes tonight. Please highlight any questions you might have and bring